Good morning to everyone. I'm María Navarro-Cáceres. I'm the first author of the work that I'm gonna present is objective evaluation of tonal thickness for chord progressions using the tonal interval space. This work has been carried out with the collaboration of Marcelo Caetano from University of Marseille and Gilberto from the University of Porto. Our work is centered in chord progressions. Chord progressions are core elements of Western tonal music. They are usually created following multiple theoretical and perceptual principles. So, how to measure if a chord is more fit or not in a tonal context? This is what we call tonal fitness. In a previous work, we created a model that tries to measure this fitness of a chord according to their own properties, the chord construction, and the relationships of the chord with the previous chord combination. In this proposal, we extend this model to take into account a new property, a hierarchical measure. We want to measure the hierarchical aspects of the musical phrase. The model proposed is capable of measuring the fitness of a chord in a progression, not only taking into account the previous chord, but also the whole context, hierarchically speaking, of course. A chord. Chords are three or more notes sounding together. This is a chord. When you put one chord and then another, you create a sequence which is called a chord progression. As we mentioned before, when you listen to chord progressions, in a tonal context, you follow some rules that allow to create some expectation. For example, when you listen to this, you feel something is missing at the end of the chord progression. We can listen again and see what happens. Now we fix that expectation. Why exactly we feel this when we are listening to a progression in a tonal context? That's exactly what we are trying to measure with our measure of tonal thickness. The objective of the tonal fitness is to measure how one chord is related to the rest of the chords in the progression, of course following the Western tonal rules. There are several theories that try to explain this, for example, Schomburg's theory, Rameau before Schomburg, or some more recent theories that are also more prepared to encode properties in a computer. For example, Lerdahl's theory, which is widely used in different proposals to model and analyze chord progressions. What all theories have in common is that tonal fitness of one chord depends not only on how you construct the chord, which notes are involved in the chord, but also how you combine them, which chords you have before and which chords you have later. The relationships between the notes that are in a chord usually modify the perception of the chord. This perception of the music, of the sounds of the chord is usually called consonance. For example, we can listen to these chords. Our tonal ears, we are speaking in a tonal context, says that one is more consonant than the other. For us, this chord is less consonant or more dissonant than the other. The consonance also depends on the notes and chords that are playing the progression, and also, of course, the context. The chord progressions are usually linked to a scale or a key which conducts the sounds of the chord. The key usually sets the context, and according to the key, a chord can be more or less consonant. We have spoken about how to construct individual chords to create a consonant or a dissonant chord. The next step is how to combine chords to create a more fit progressions. We are listening to the two examples. We have the same chord, but in a different context. We can feel that the expectation that we create in each example is different. Well, we have a feeling of full resolution. Even if the chord is the same, the context changes and also the expectations, the tonal fitness. How to measure the relationship of one chord in the chord progressions? There are some theories, as we spoke before, and all that they have in common is that we have to look to the previous chord and also to the whole context. This context is usually measured like a hierarchical structure with the chord progressions, and we have to measure not only the distances between the chord, but also the hierarchical distances between one chord and the rest. When we speak about hierarchy, immediately we think about trees. We have trees to structure relationships in family, in the cover, in whatever organization that we can think. Music is also structured, and this can be represented by trees. To understand better how this works, we will make an analogy with linguistics. In some languages like English, French, or Spanish, the structure is important to construct phrases, to construct sentences, and we usually apply trees to represent and analyze the syntax of a sentence. For example, we have a sentence that can be divided in subject and predicate. Predicate can be divided in verb and a complement, and the complements can be also divided in some words. So, for example, we have for the subject a personal pronoun, for the verb one verb, for the complement of a noun phrase. We have a determinant, then an adjective, and then a noun. And we can create a phrase with that. Of course, we have a lot of suggestions, but for example, we can use I am an intelligent girl. Because we have some parts of the phrase that are more important than other parts to understand the meaning. So, for example, if we remove an intelligent girl, even if the phrase is not completely correct, we can grasp very easily the meaning, I am a girl. If we remove the important parts of the phrase, we can lose the sense of the phrase. For example, if I remove the verb, I cannot understand very well the meaning. I an intelligent girl. I what? I met, I know, I am. We don't know very well. The same happens for the music. All chord progressions have an internal structure that could be represented with a tree. So here we have a phrase, we can have subject and predicate, in this case two semi-phrases, and each semi-phrase can have some complements. Finally, we have words. Here we don't have words exactly, we have chords. Each chord has a syntax, and this syntax is translated into a tonal function, like a syntax function. And this tonal function depends on its construction and the context in which we have the chord. So in this case, we can listen to the chord progression. Okay, we understand very well the phrase, the musical phrase. It has sense, and the same than in linguistics. Now, if we remove the wrong parts of the chord progression, if we remove the right parts of the chord progressions or the minor parts of the chord progression, we can keep the meaning of the progression. For example, okay, we have removed this, and the sense of the phrase is more or less the same. We have start, we have tension, and we have resolution at the end. Contrary, if I remove the wrong parts, don't have this feeling of going up and down. We only have a feeling of maybe going up and finish. So we have lost the sense of the phrase. To construct and analyze trees, there are different theories. For example, Rohrmeyer proposed a grammar to model chord progressions. We use this theory in our work, as we will see in a later slide. Well, now you can say, oh, that's very beautiful theory, but how to encode all this music stuff in a computer? We need to represent any musical element somehow and transform the musical properties into numbers. One way is to represent music in geometrical spaces. In the literature, we can find some proposals, and we selected tonal interval space. The tonal interval space is a space that can transform chords with a discrete Fourier transform into points in a space. So we have 4 chords, and we can compute distances between chords as distances, Euclidean distances between points, knowing that these distances captures musical properties like perceptual similarity. The advantage of this particular space is that we can compute not only chords but also scales, tonal functions, and particular notes. So, as we can represent different pitch configurations, we can also compute different distances between points. So our contribution, as we spoke in the first slide, is that we use the hierarchical structures presented by trees, we use the tonal interval space, and we use the harmony theory that we explained before to create a model that is able to compute tonal fitness for one chord. Our model basically takes as an input a chord progression. The model measures the tonal thickness for this chord progression according to 4 different properties that we proposed, and then the model obtains a rating for each chord of the progression measuring the tonal thickness. If we join the points, we can get like a curve or a function which is usually called tonal fitness profile. So first of all, what is a surface dissonance? Well, we consonance. The surface dissonance tries to measure the consonance of a chord, meaning the construction of the chord. How to compute this in the tonal interval space? To calculate the distance, we calculate the distance between the most dissonant chord, which is that one, and our particular chord. So, mathematically speaking, this very dissonant chord is the center of the space in the tonal interval space. So we calculate basically the distance between the center of the space and the point corresponding to the chord. We have the surface dissonance leading, which is the voice leading. As we can observe, the chords usually have the same numbers of notes. The path that the notes can trace horizontally is called voice leading. We measure this property by calculating the distance between the notes and the previous ones in the same voice. So we calculate the distance between the first note of the previous chord and the first note of the present chord, the second with the second, the third with the third, and the fourth with the fourth. Also, we calculate the distance in the tonal interval space of the particular notes and the key, so the context in the chord progression. So we measure the dissonance, the particular chord construction, we measure the voice leading, we are speaking about individual notes, and now we are measuring the distance, the perceptual distance between the chord. What we want to capture with this property is the tonal thickness of the chord according to the immediate musical context. The immediate musical context is the previous chord in yellow, the key that we have, and the tonal function between the chord and the tonal function that it has to develop. Remember, this is similar to the syntax function of a sentence. Finally, we have to measure the chord in the hierarchical structure. We have theories to create a progression from a tree. The problem for us was how to create a tree from a given chord progression. We created an algorithm that reversed the rules proposed by Romeyer to inversely construct a tree. So we have at first chords, which are the words, and we create a hierarchical structure to have at the end a phrase divided in subject and predicate, and so on. So additionally of that, we have to calculate which chords are the dominant ones, meaning chords that are more important hierarchically speaking than others, which chords has the fundamental syntax function for this musical phrase. These chords are essential for the progression and cannot be replaced. When we calculate them, we have we have to measure how these chords influence the tonal thickness for the chords that we want to measure. For example, if we select the chord number 2, we want to know the relationships between this chord and the rest of the chord progression hierarchically speaking. So now with these three we can calculate the hierarchical tension. How? First, we calculate the distance between the chord number 2 and the dominant chord, the chord with more important syntax function. Then we calculate the distance between this chord and chord number 5, which is hierarchically more important, and finally the first chord, which is the most important chord in the progression. We have created a model that, given a chord progression, is able to get some ratings for each chord according to their tonal thickness. What we want to know now is if our model really captures musical properties. So the first question is, how can we evaluate the model? According to the literature, we thought that the best way to do that is by designing a listening test. So in the design process, we have to wonder which progressions can we include, how to capture fit and unfit chords, and of course, how to know if different keys and tree influence these results. So, summarizing, how did we select the stimuli? Considering everything, we created two different tree structures, and for each tree, we create a total of 30 chord progressions of 3 chords each chord progression. They can belong to two different scales or two different keys. The first 2 chords are fixed and the third changed. The fitness of the third is framed between very unfit and very fit chords according to our model. The question that we posed for the listener was how well the third chord follows the first and second. We have 4 pages of options in our listening test, 1 per tonality, 2 per tree. And the listeners have to rate if the third chord fits in the progression following a 5-point scale between very bad, this is very unfit, to very good, very fit. They can listen to the progression several times and they were presented randomly. And finally, we have 48 participants that took the test. These are the 2 trees that we constructed for the chord progressions. We have selected one option just for illustration to know how they could sound. The first option. And the second one. Here we can listen that maybe in the first one you can listen to some kind of resolution at the end, and in the second one it's not resolution at all because the trees are different. The hierarchical structure between the chords are different. We compare our model with the subjective values that we have. So we made our regression between the subjective evaluation with the listeners and the objective values that we we got with the model. The regressions values were very positive, and also we compare our work with our previous work, which only considered the linear constraints and the immediate context, and Lerdahl was we consider also hierarchical tensor, but in a different geometrical space. So the high values for the regressions indicate that the subjective ratings correlates very well with objective values. As we can see, these results confirm that the model captures tonal fitness very well, and of course better than the others, even if the others are related also. We can conclude that given a chord progression, our model is able to capture musical properties and construct a tonal fitness profile for the chords. The results that we retrieve prove that the model corresponds quite well to subjective perception of the listeners. Our contributions can be summarized as follows. First, we constructed a model that captures the tonal fitness according not only to the previous chord or the consonants, but also with other properties like, above all, hierarchical structure in a chord progression. We also develop an algorithm that is able to create a tree based on the chord progressions. And also we can say that the model is a good indication for tonal fitness, or a better one according to our statistical results than other models proposed in the literature. For your attention, thank you to be here, and I'm here to answer any question that you may have. Thanks very much.